differentiating the quotient of two functions. Our objective in this lesson is to differentiate the quotient of two functions. Now, just like when we try to take the derivative of a product and we need a special rule, the product rule, when we are taking the derivative of a quotient, we also need a special rule, the quotient rule. The derivative of f of x divided by g of x, as long as g of x does not equal 0, is g of x times f prime of x minus f of x times g prime of x divided by g of x function squared. Using Leibniz notation, the derivative with respect to x of f of x divided by g of x is g of x times the derivative with respect to x of f of x minus f of x times the derivative with respect to x of g of x, all divided by g of x squared. You'll notice this looks very much like the product rule, but some things are very different, such as in the product rule, we're adding. In the quotient rule, because a quotient, which is dividing, is a fast way to do subtraction, we are subtracting. Also, whereas the product rule has no denominator because it's a product, the quotient rule, which has a denominator in its derivative. For fun, and because there's a neat little song that goes with it, if we think about f of x, the function in the numerator, as the function that is high, the high function, and the function in the denominator as the low function, then our quotient rule looks like low, d for derivative, high, minus high, d for derivative, low, over low, low. If you ask me in class, I'll play you the song. Low, the denominator's function, times d high, the derivative of the numerator function, minus high, the numerator function, times d low, the derivative of the denominator function, over low, low, the denominator function squared. Let's take a look at applying this quotient rule. Find the derivative of each function. 1. Y equals x squared plus 1 divided by 2x minus 3. This is a quotient of two functions of x. So when we do the quotient rule to get dy dx, we can think of low d high. Low being the denominator function comes first, 2x minus 3, times d high, the derivative of the numerator function, 2x, minus high, the numerator function, x squared plus 1, times d low, the derivative of the denominator function, which is 2. Over low, low, 2x minus 3, quantity squared. Now, while that is a derivative, it of course can be cleaned up a bit. So let's do that next. So we distribute the 2x, and that becomes 4x squared minus 6x, and we distribute the 2, and of course we're subtracting, so minus 2x squared minus 2 over 2x minus 3 quantity squared. And then we can combine some like terms here, so we get 2x squared minus 6x minus 2 over 2x minus 3 quantity squared. Now, of course, this only works as long as the denominator is not 0. So to make sure we don't want that denominator to equal 0, that means x cannot equal 3/2. Examples 2 and 3 are quotients. However, these are two examples where, while we could use the quotient rule, we wouldn't necessarily choose to use the quotient rule. Let's see why not. F of w equals w squared plus 5w divided by 2. We can rewrite this so that f of w is 1/2 times the quantity w squared plus 5w. And now we simply use the constant multiple rule. F prime of w, the derivative, equals the constant multiple times the derivative of that function of w, 2w plus 5. That is an acceptable answer, or we could rewrite that the way it was originally written as 2w plus 5 divided by 2. In number 3, we do have a quotient of two functions of t, and unlike this one, that denominator can't be pulled out to be a constant multiple. But in this case, what we can do is distribute that monomial in the denominator. So we have t squared divided by t plus 5t divided by t. That makes our function s of t equal to t squared divided by t makes t, and 5t divided by t makes 5. Therefore, when we take the derivative, we don't have to use a quotient rule at all. S prime of t equals the derivative of t, 1, plus the derivative of 5, 0. Or just 1, to be nice and short. Now, a corollary to our quotient rule theorem is the derivative of the reciprocal function. This is a quotient, 1 divided by g of x. And if I use the quotient rule on this, I'll get negative g prime of x divided by g of x function squared. Of course, I can use the quotient rule anytime I have a quotient. But if we remember this derivative of the reciprocal function corollary, then things might work a bit faster. So let's try quotients that can be considered derivatives of reciprocal functions and try to use this shortcut. In this example, f of x equals 1 divided by 1 plus x squared. We can see this as a reciprocal function, so when I take the derivative f prime of x, using my derivative of the reciprocal function corollary, g of x is the denominator, so my derivative has negative g prime of x in the numerator, so the derivative of 1 plus x squared is 2x, negative of 2x, divided by g of x function squared, 1 plus x squared squared. A quick way to the answer. Of course, I could have used the quotient rule and have come to the same conclusion. Either way would work just fine. Number 5 says h of x equals e to the negative x. First, I want to think of this h of x as 1 divided by e to the x. Now, I could use the quotient rule or use this corollary for the reciprocal function, since this is the reciprocal of the function e to the x. Using that reciprocal function derivative, h prime of x equals negative of the derivative of that function e to the x, which is just e to the x, divided by e to the x function squared. While this is the derivative, this can be cleaned up quite a bit. Let's see how. Negative e to the x divided by e to the x squared makes e to the 2x. And because these have the same base, I will subtract the exponents. Negative of e to the x minus 2x, which makes e negative e to the negative x. Number 6, g of v equals 3 divided by 4v to the 5th. Now this time, notice these constants hanging out all over the place. Let's see how we can rewrite this to make it a little bit more approachable. 3/4 as a constant multiple. I'll pull that out. And the v to the fifth, I'm going to bring that up. 3/4 times v to the negative fifth. This is a power function. We can use our power rule. This is a constant multiple. We can use our constant multiple rule. So I don't need to worry about any quotient rules or reciprocal function rules either. Let's take the derivative of g of v or g prime of v. Constant multiple rule tells us the 3/4 hangs out, and the derivative of v to the negative fifths, negative 5v, subtract 1 from negative 5 and get negative 6. And then maybe we can clean this up a bit to make negative 15/4 v to the negative 6. And then sometimes we'll see this written how it originally was written with no negative exponents. So we'll say negative 15 divided by 4v to the 6th. Thanks for watching.